Villegas. And we will talk about hypergeometric functions.
Thank you. Right. So the goal, my goal in talking about this, is to be able to compute with higher degree L functions. So, and I owe this goal to Brian Conry, who asked me if there was a way to do this. So just to be safe, what we're talking about, an L function for me looks like this. I'm sure it does for you too. So n is the conductor, Lp of t is a polynomial, and I'll look at situations like this where for almost all primes the polynomial has that shape where the inverse Frobenius roots have a fixed size w. So I want to assume that my polynomials have integer coefficients. So so for p not dividing n, they look like this. W will be the weight, the degree. So this L series is expected to have a functional equation that has this form. So for d equals 1 is directly L functions, we all know. At d equals 2 are modular forms of the usual kind, like for example, way 2 would be L functions of elliptic curves. I think I need something, right? Huh? Oh. Oops. And then. Okay. So I stop it with. Okay, good. So we really want to try to see if one can compute concretely and numerically with L functions of this kind for d bigger than 2. And just to give you a sense of what we're dealing with, of course, you can associate such forms to automorphic data. But so this typically means that you have to describe some finite dimensional vector space, describe the action of Hecke operators on the space, and either search for a particular sequence of eigenvalues that you might have, or find, say, eigenvalues that are rational numbers. But even so, according to Paul Gunnels, who's sort of a bit of an expert in this, if you try to do something for SL4, you're lucky to compute one Hecke operator. And so this quickly becomes very difficult once you pass the comfortable world of d equals 1 or d equals 2. And I'll mention another such instance in a little bit. For Siegel modular forms, you are more successful, but you can go very high in the conductor n. So on the Galois side, you can look at the cohomology of some smooth, say, smooth projective variety, and look at some appropriately cut subspace and look there. But again, just to have the context in mind, so bear in mind that, say, if you look at quintics in P4, which would be the analog of elliptic curves in dimension 3, so this will give you threefolds, Calabi-Yau threefolds, then the middle cohomology has dimension 204. So unless you pick your quintic in any kind of reasonable way, you're never going to find this L function. And this, in a sense, is what looks like a simple extension of what we know what to do with elliptic curves. So you can expect to do things like this, but you have to sort of search for your V somewhat intelligently. And so what I want to talk about is a collection of such V's that arise from the world of hypergeometric functions. And I hope you allow me to be a bit speculative. I will mostly report on the way things seem to work. I'm not going to be able to necessarily justify a lot of the things I'll say, but it's backed by quite a bit of numerical evidence, so I'm confident in what I'm saying. So those are the hypergeometric motives of the title. And just to give you a sense of where this comes from, so in 1958, Igusa noted the following fact. So if you take the Legendre family of elliptic curves, Doring had already computed an expression for the Hasse invariant as a sum involving binomial coefficients. R here is p minus 1 over 2. So this is the number of points of this elliptic curve over fp is p plus 1 minus a p lambda mod p. And what Igusa noticed is that a p lambda satisfies the same differential equation, order 2 linear differential equation, satisfied by a period of E lambda over the complex numbers. So that it's interesting that the reason he wanted to do this is because therefore the polynomial cannot have double roots, and you can count the number of elliptic curves mod p. But this observation had incredible far-reaching consequences. I think it's fair to say that a huge amount of the work of Dwork is a great elaboration of this observation. And that's going to be also our starting point. So to be precise, the period in question, let me write it like this: u of lambda is a hypergeometric function of the style of Gauss, an ancient object. And that if you take an appropriate cycle on this curve and an appropriate holomorphic differential, it integrates as a function of the parameter, which is this. And this equation, this series satisfies a second order linear differential equation, as I said. And both the polynomial mod p and the period over C satisfy the same equation. So, well, what happens in general? The world of hypergeometric series goes into things of this kind. This is a classical notation. So we have numbers beta 1, alpha 1 through alpha d, beta 1 through alpha d minus 1. You define this to be this series. And it's classical, a little annoying that classically there really are also d parameters beta, except one has been fixed to be 1, and that gives rise to this n factorial. So this satisfies a linear differential equation of order d. The one up here, this binomial coefficient, you have to write it into this Pohammer notation, which, by the way, is simply the product of the rising factorials. It's the product of numbers going up like this. So for the Legendre family the parameters are 1/2, 1/2, and 1, 1. So the 1/2, 1/2, if you convert it into this binomial notation, gives you that 2n to n squared. Okay. So let's see if I get this. So another famous example of this connection is the dwarf pencil. Let me use the case of the quintic, which is also quite famous in the context of mirror symmetry. So if you look at this F43, which has parameters 1/5, 2/5, 3/5, 4/5, and 1, 1, 1, then this is associated to the family of threefolds given by this equation. And here there's already something happening, that the parameter t I want to use is actually the parameter psi to the -5th power. So here we have one instance of what we were saying. The middle cohomology of this is 204 dimensional, but it has a large group of automorphisms. So if you look at the subspace, say V psi, fixed by the automorphism of sin xi to zeta I to the x to xi, where zeta I is a fifth root of unity, and the product is 1, then this visibly acts on the threefold, and it acts on the cohomology, and it fixes a 4-dimensional space. And that has a period. So if you pick a form and a space, you will find and integrate an appropriate cycle, you're going to see this hypergeometric equation. So here's an instance where you can cut out something small that is you can handle geometrically. Now, so what happens? What's the connection with L-functions? Well, what I claim is that there is a formula for the trace of Frobenius acting on psi of B psi, which has a form like this. I'm not going to write it explicitly because it's not quite necessary, just to give you a sense of what it is. It's basically a, let me write it in general. I'm including the last beta to be 1 or whatever it is in general. There's a Jacobi sum. So you can express it as a p-adic formula if you where p is the same p associated to q. So this is a Jacobi sum, and this precise form of this is something that Nick Katz wrote in one of his books. So what I'm claiming here is that there is a formula to compute the trace of Frobenius acting on this space V psi, for example. Now the alphas and betas will have to be the ones for that case. But in general, the claim is that there exists a family of motives which I call H alpha beta T, which is defined over Q. So if you pick your parameter T to be in P1 of Q minus 0, 1, and infinity, it will produce a motive over Q. And this leads to an L function of degree d and a weight w, which I'll explain how to compute. So let's see if I may make myself clear. So if we take the example of the quintic, for example, I claim that there's a formula to compute the trace of Frobenius on that four-dimensional subspace by means of a formula like this that involves Jacobi sums. Now what I claim is that ignore the quintic altogether and stay with this. I claim that there is a motive that lives somewhere, which we don't need to know exactly where it is, for which the trace of Frobenius is given by the analog formula. So if you apply this to the Legendre case, this is a p-adic form of the Doring's calculation. So if you look at this expression modulo p, then we'll give you the polynomial that Doring found for the Hasse invariant. But this is not mod anything. This is actually p-adic, so it gives you the trace of Frobenius as a p-adic number. I mean, so we're computing an integer, but we're computing it as a p-adic number. Yeah. D will be, in the case of the quintic, is 4, is the dimension of the space that we're dealing with. Here, D is whatever D is you want. And what I'll do is explain, well, give you some sense of what these motives look like in more general examples of them, other than the ones I mentioned. And, well, I'll first explain that this is a situation of what Katz calls rigid. And so what this means is that the differential equation, well, or the monodromy, as I'll say in a minute, is completely determined by these parameters. There's no moduli. So ultimately, what I like to, the sort of driving force here is that anything that we want to know about this L function should ultimately come just from this small amount of data, this collection of alphas and betas. And of course, that philosophically, it's tautological, that's the case, but how do you actually go from the alphas and betas as input to data about the L function as output? So I'll try to tell you the things I know about that. Okay, so what? So let's do. Well, let's do the classical. Let's discuss this differential equation in the classical. So the classical incarnation of this motive is simply the differential equation. So how does that work? Well, we take V to be the space of solutions to the differential equation. There are regular, so holomorphic, say at some point that is not 0, 1, or infinity, which are where this differential equation has singularities. So that's a space of dimension D. And if you start, so we have 0, 1, and infinity are the singular points of this differential equation. So if you start your solutions at a half and you follow a path, then you can analytically continue the solution and you come back to another solution which might not be the same. And that process gives you a map from pi 1 of p1 minus 3 points to the general linear group on the space V. And this is the monodromy representation. So how do we understand what this is? Well, as Peter will tell you, the actual group is very difficult to understand. But we can understand what happens if you take a little loop about one of the excluded points. Then it's going to map to some element HS in GLV. And the nature of that local monodromy is completely determined by the parameters that we gave. I'm getting the hang of this. So since pi1 of E1 minus 3 points is generated by these 3 loops with the relation that the product is 1, this group, this representation is characterized, it's, well, gives by the nature of H, the 3 H's that we get, and the product has to be the identity of V. And the point is that this is, as I said, something which Nick Katz calls rigid, which means that if you give yourself, so in this case, it's enough to know what is the characteristic polynomial of H infinity and H0 to completely determine this representation up to conjugacy. So I'm going to call this Q infinity and Q0. And the connection between the parameters, alphas and betas that I had before, is that the characteristic polynomial has roots, the exponentials of these numbers. Okay, so the point of rigid then is if you give yourself these 2 polynomials, then this uniquely characterizes this this representation up to isomorphism. So if you locally conjugate each one of these elements, there is a global element that does the conjugation. So that's what I was saying before, that there's no parameters involved in this. In order to describe, to give this representation, all you have to give is this data of Q infinity and Q0. And the way it's going to work to get the kind of things that we want is that we want to assume that these polynomials are integral. They have to have, let's just call them cyclotomic, meaning that their roots are roots of unity. And we also want to assume that they're coprime. This will exactly mean that the representation rho is irreducible. So that's the data. You just have 2 cyclotomic polynomials of the same degree, D, which are coprime and have roots of unity as roots. So out of this comes out a family of motives over Q of degree D. And so the task, if we choose to accept it, is to get everything possible of these motives out of this simple amount of data. What I mean ultimately for me is all the data that is required to have an L function. And what I mean by this is that I like to be able to put this data in the computer and verify, for example, that the resulting L function satisfies the functional equation, which is a highly non-trivial statement. I mean, it's not going to, you're not going to prove that it satisfies the functional equation, but you can be happy that it looks like it does. And believe me, if you mess up even the slightest thing, the thing fails completely. So if numerically it looks like you have the functional equation, you can be pretty sure that you're doing something right. Okay. So how do we unravel things out of this data? So again, just to keep tabs of the examples, if we look at the Legendre family, then the polynomials are simply t plus 1 squared for Q infinity, and Q0 is t minus 1 squared. The parameters are 1/2, 1/2, and 1, 1. For the quintic, the polynomials are t is the cyclotomic 5 polynomial for Q infinity, and Q0 is t minus 1 to the 4th. Okay, so let me show you how we can compute the weight of this motive. And this, I sort of rediscovered it, but it is something of Portier and Golishev, and they conjecture the formula works in general, and they have a significant portion of examples where they can prove it. So now, so the goal is to somehow take this data and extract the information we want, and this will be a purely combinatorial calculation, which I think, well, I think it's interesting. So let me give you some details of how it goes. So the data could be given in various equivalent forms, and some forms are more convenient than others. So let me write this data as follows. The rational function q infinity over q0, it's if you write the cyclotomic polynomials in terms of these guys, you can write it like this for certain numbers gamma nu, which are integers, and all but finally many are 0. So another equivalent form of giving this motive is just to give the numbers gamma nu. And out of these numbers gamma nu, I'm going to form a periodic function in the reals. So I'm going to call L of x, and it's the sum of gamma nu fractional parts of nu x minus a half. So if we take the case of the quintic, for example, you'll see, so this function is going to be locally constant and periodic of period 1. And if you look at the case of the quintic, it looks like this. So it's right continuous. It looks like this. And the breaks are exactly at the numbers alpha and beta. So basically, you can also describe it as say, well, if you see alpha, you go up, and if you see a beta, you go down one step. So it's integer valued, and it's locally constant and right continuous. And so the point is that this height is the weight plus 1. Okay. So in this case, it's 3. The weight is 3. And that certainly is consistent with what I said before, that this thing happened to be living in H3 of this threefold. Okay. Now, if I have time, I'll mention something about the Hodge numbers, which is another data we need. So the L infinity part of the L function is controlled at first approximation by the Hodge numbers of the motive. And this will also come from some combinatorics of this function. But I might say that something about that later. Okay, so let me give you my favorite example of this motives, which we can blame Peter again for this. So this is the Chebyshev example. So I take q infinity to be the cyclotomic 30 polynomial and q0 to be phi1, phi2, phi3, phi5. You can check that these are two coprime polynomials of degree 8. You can write q infinity over q0 as t to the 30 minus 1, t minus 1 over t15 minus 1, t10 minus 1, t6 minus 1. Right. And the corresponding hypergeometric series up to scaling of the variable, you can read it off from these numbers here. And the reason I call it Chebyshev is because these numbers are the ones of Chebyshev to use to almost prove the prime number theorem. So there's some constant k, scaling factor. Now, it's a nice little thing to try to see what is the function for this case. And what you'll find is that the function looks like this. Okay, so it has 8 jumps, and it goes between -0.5 and 0.5. So that means that the weight of this is, this height is 1, so the weight is 0. And what does that mean? Well, weight 0 exactly means that this series, this hypergeometric series, or any solution to the differential equation, is algebraic as a power series, so it satisfies a polynomial in 2 variables. Or what is the same is that the motive is Artin. So what this means is that this example should then be associated to, so for a choice of the parameter t in Q, we will get an Artin L function of degree 8. And the underlying monodromy here, the image of the monodromy map, is actually the Weyl group of E8, which is enormous. So this would be, to me, a real challenge if I could ever manage to get an example where I can compute the L function that is associated to one of these instances. Okay. Now, if you're curious, don't try this at home, but if you want to find the function, it satisfies an algebraic equation. And if you're as naive as I was when I first thought of this, I thought I would just write it down and find it. But the degree is actually of the order of 483,000. So it doesn't seem likely then. Okay.
Do the things that Sylvester tried to improve over Chebyshev, do they have meaning? The connection with Chebyshev just make
I think to a large extent, I think is a red herring. So from this point of view, the interesting collection is this: the cases of weight 0, and those are the cases where the monodromy is finite, and those were classified by Berkes and Heckman. And there's going to be similar things like this associated to them, but they don't seem to have a great relevance to the Chebyshev idea. At least I can never find it. So it's somewhat of a red herring. So now, one of the things that makes these things computable is that, of course, it's far from a new idea, but the fact that they come in a family, so there's a parameter t, is a crucial thing. So let me tell you what the heuristics are for the computation of the bad Euler factors. So the good Euler factors we can compute by that formula that I mentioned before that had the Jacobi sums. And that doesn't require any description of this motive other than the data that defines it. But it doesn't allow you to get what the bad Euler factors are, or, for example, what the weight which I describe, or the conductor. The conductor is the hardest thing to pin down. I don't know how to do it in general. But let me tell you how I think is the way things go. So the answer here is that the local monodromy gives the action of inertia. And so this is a leap of faith that perhaps somebody could explain to me, but because these are a priori completely different things. We have the geometric monodromy that has to do with analytic continuation about a point, and we have the action of Frobenius, the inertia group on the motive on arithmetic side. but this seems indeed what is happening. So for example, for the quintic, to give you an example, the monodromy at infinity, the characteristic polynomial was the cyclotomic 5 polynomial. So that means that in this hypergeometric world, all the monodromies have as large Jordan blocks as they're allowed. So what it means is that, well, in this case that doesn't apply, but this is actually diagonal with these eigenvalues, so it's conjugate to this. So which means that if the parameter t is a fifth power, which will happen, for example, if you look at the quintic pencil, because there it's psi to the fifth. So if you pick up psi to be rational, then this is a fifth power. So the effect of that is that you have to take this matrix to the fifth power, so it's the identity. And so what happens here is that so you have a prime p that divides the denominator. So then your motive looks like if it's sitting above infinity at p, and therefore if it's a fifth power, then the thing is actually smooth, and you get a degree 4 L factor. And that, if you look at the quintic, it corresponds to psi equal to 0, and you get the Fermat quintic, which is certainly a smooth threefold, and that's the corresponding Euler factor you should use. But so what I'm trying to show you is how the understanding of the local monodromy impinges on the nature of the Euler factors for bad primes. At least the primes that are tame, like p equals 5 for the quintic, will be a different story. So again, continue with the quintic. Q0 is t minus 1 to the fourth. So that means that the H0 is conjugate to a full Jordan block. And so here, the fix of this has dimension 1. And because it's one Jordan block of size 4, it should reduce the weight from 3 to 0. And so here the Euler factor then is just 1 minus t. And again, this is what this seems to be the case in practice. And if we look finally at what happens at H1 is a reflection, but we are in the symplectic case, so it actually is a transvection. So I was saying reflection in a general sense of fixing a codimension 1 space. So its Jordan form looks like this. So the fixed space has two parts, one corresponding to this Jordan block and the other corresponding to these two other blocks. So this will have, the fixed part has dimension 1 and 2 here, and the weight is reduced to 2, and this one is 3. So what it means is that the Euler factor will look like a linear factor for some character epsilon, and a degree 2 Euler factor. And so here for the quintic, this is the symbol 5p, and this is a modular form of weight 4 in gamma 0, 25. I think this is something that Chad Schrent proved in his thesis, that this piece is actually modular and is associated to this modular form. So it's just to give you a flavor that this, at least for me at the moment, a heuristic reasoning actually does give you a way to describe, to some extent, what the Euler factors look like for the bad primes. It doesn't give you the full story, because this just tells you that it factors this way. You still have to figure out what these pieces are. So And what I expect to happen is that all these motives should share quite a number of features. So by trying to understand some explicit examples, I like to see what can I say about the general case. Yeah.
I'm not sure to understand. You have a conjectural VCP to go from the local monodromy
Yes.
to the inertia.
Yes. This is for primes p that are tame, and so p does not divide the denominators of alpha or beta. Those are going to be Weyl primes, and the story there I don't have a very good clue. So, for example, this story will happen if you have a prime p that divides t, but doesn't divide the denominators of alpha and beta. So, because if p divides t, t is like 0 mod p, and so then the story will be controlled by the monodromy at 0. And if p is congruent, if t is congruent to 1 mod p, then we're in this situation, and the bad Euler factor will look like this. This is what I know in practice is how it works, and I love to understand how to justify this.
P squared divided P inverse is still tame?
Yes. Yeah, the wild ones are the primes that divide the denominators of alpha and beta. In the quintic case, that's only 5. Right. Okay, now let me show you an example where I can be more specific and less speculation. I wanted to, in route to try to compute the case of Chebyshev example, I wanted to start with an example of an Artin L function that was easier to deal with. And in the Berkes and Heckman classification, there's an infinite family that corresponds to the AN cases. And those all give you symmetric groups and not very interesting L functions somehow. So I'm going to move to the next case. So this example is what I mentioned in the title, has as Galois group the Weyl group of F4, which is a group of order 152. So, I mean, if you think about it, what I'll be claiming is that we have an extension of Q, depending on a parameter T, of order Galois extension of order 1152, which has a 4-dimensional representation, and I want to compute the Artin L function of that representation. It seems unlikely that you're going to be able to manipulate this field, so something else would be necessary. So here, the parameters are this, and I'm just pulling this out of a hat, or you can look at the classification of Berkes and Heckman and see that this corresponds to this case. I mean, there's a way to think of this, which I could explain. Just I'll give you this to taunt you. This is the diagram of F4, and you can get these pairs by picking one node in this diagram. So if you do that, in other words, this Q infinity is actually a Coxeter element in this group, and this other one is a Coxeter element times that reflection. So so here you can write down the corresponding hypergeometric series. It will be of the style of Chebyshev, something like this. And then there's some constant t to the n. And this satisfies an equation which is a little bit more manageable, is of degree 96. Okay, and so the Galois closures, if you adjoin to Q of t this U, and you look at the Galois closure, that will have Galois group WF4, which is of that size. And somehow the Artin L function will be coming by taking a particular t. So generically, if you pick a t in Q, you will find the corresponding extension of Q with that Galois group. And what this motive is the corresponding Artin L-function associated to the reflection representation of WFA4. So I thought that this should be something doable. And again, in all of these cases, it's easy to write down the good Euler factors. You can get a sense of what the weight is. We know it's 0. Even here, the case of the infinity, the gamma infinity is not clear, because I mean, you can compute the Hodge numbers in a way that I alluded to, but that doesn't tell you the full story if the weight is even. Yeah. 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 Well, I mean, certainly is something I was going to say. We did some work with this with Enrico Cohen, as you say, by the way, who's my co-author in this. And we did something like that, very naive. But I'll say it now. If you know almost everything about an L function, then you can use the L function to try to find the things you don't know. And so we've certainly used this significantly, but on a very sort of naive form. Sorry? Oh yes. So I mean, it's not like you take it out of the box and it just works. You actually have to be a little clever to do it. But we want to be clever, so possibly we'll use an approach of Booker. But anyway, that's certainly crucial, because it's actually, for example, the conductor is very difficult to get. At least I have no idea, or no even the most heuristic possible way to think of what the conductor will be, other than what its prime factors are, of course. But the heuristics that I mentioned are very useful to cut down on the unknown Euler factors, for example. Now, in this case, as it'll turn out, we'll be able to, at least again, not fully prove, but we're going to be able to completely describe this L function, in spite of the fact that the degree of this field is so large. And so here comes an observation. So Henri Cohen, what he did is took the formula, this p-adic formula with the Jacobi sums, and just said, okay, well, what could this be counting? And he sort of back engineered from that formula to write down an equation of a variety which has in its counting the same number. Okay, and in a way, that's more or less what Katz does. You know, Nick, he does this for completely for rigid motive, rigid equations in general. You somehow you can produce your motive inside the cohomology of variety. And the thing is that it doesn't necessarily means that it's going to be of help to have that, but the fact that it can appear in several different places, you can exploit that. So this we know a priori what it is. It's the Galois closure of this 96-degree polynomial, but that's unwieldy. So what Henri does is sort of ignoring anything that he knew about this. He unraveled what the trace function was and came up with a cubic surface. So the upshot is that this motive of degree 4 is actually also sitting inside the middle cohomology of a cubic surface. And this is an open cubic surface. And you can write down the equation. I mean, he has this. I mean, his computer does this. And maybe at the first go, you get some horrible equation, and you still have to manipulate it to get it perhaps in a more decent form. But you get this open cubic surface. And this we know since Manin that the cubic surface has 27 lines, and there's an interesting Galois action on the 27 lines. He showed that the symmetry group is the Weyl group of E6, and Saito, I think, has been proposing to study these Galois representations on lines on cubic surfaces and similar things for quite a while. So this week sort of fell in our laps. Now, this is actually a little more interesting than just the old cubic surface, because it's affine. So what is actually missing is 3 lines. So this cubic affine surface actually has 24 lines. And so in order to understand this Galois action, it would be useful to know how these lines are, how they behave. So the precise form is that the number of points of this surface is some simple polynomial in P times the trace of Frobenius on this hypergeometric motive. So it's been Tate-twisted to live in this H2 of the surface. And so I'll finish with this a little bit of geometry here, which is I think is quite pretty, of a description of these lines. So if you notice, the variable y is sitting all by itself in the equation. So if you project to the xw plane, you get a cubic curve. So in the xw plane, you get a cubic curve, and with a line missing in affine space. And so this is this cubic curve, and then there's a line, which cuts it in 3 distinct points. So the lines on the surface will map to lines on the plane, on the xw plane. And so there's some lines on this plane. And you have to follow how this goes, but you'll discover that this is sort of a degenerate case of the bitangents of a quartic. So what it is that the lines have to go through these points, and they also have to be tangent to the cubic. And so there's 3 ways. For each point, there's 4 lines that are also tangent to the cubic, because it's like taking the square root of a point in an elliptic curve. So what we'll see is that there's 4 lines through these 3 points, and then you have to pull them back to the surface, and then they become the 24 lines, because it's a 2-to-1 map to the surface. So this sort of pull back to the surface, you give you 24 lines. So that means that you can describe where these lines live in 3 steps. First, you have to find the equation of these 3 points. That's a cubic equation. So if you are already specialized at some value of t, you have some degree 3 extension to get these 3 points. Then you need to solve a quartic equation there to find the 4 lines. And then you have to take a further degree 2 extension to go up to the surface. So that gives you this degree 24 extension, which sits inside the WF4 Galois extension. And this is sort of the smallest, 24 is the smallest permutation representation which is faithful for this 4-dimensional reflection representation. And so this realizes it explicitly. And I want to finish with this. So where is our L function appearing? Well, you have to sort of decompose this permutation representation into its irreducibles, and it has 1 copy of the complex reflection representation you want. And so what you see is that if you take the ratio of the top zeta function divided by the intermediate one, that's a degree 12 L function, and our L function divides it. So actually, that's extremely useful, because computing zeta functions of fields I consider that to be as easy in this game. And so that means that the Bayer-Euler factors, for example, have to divide the Bayer-Euler factors of this, and those are easy to compute. And so that gives you an upper bound on what they could be like, and also gives you an upper bound on the conductor. So this information is actually very useful. But at the end of the day, what happens, we ended up with a completely heuristic. At the moment, heuristic. We haven't been able to sit down and work together again. Description of this, of the full by doing some simple manipulations with ratios of zeta functions. So in the end, we don't have to do any guesses. But the hope is, in having been able to work out this case in detail, to use it, to understand this features, in order to use that understanding for other more sophisticated cases. Yeah, so so the thing is that the conductor is, the primes that divide the conductor are the ones that divide t inverse, or 1 minus t. So so apart from 2 and 3, which are the Weyl primes, you can control the conductor by having few primes in those 3 expressions. So for example, the easiest case in all of these modes is to take t equals minus 1, because then you only have 2 to worry about as an extra prime. But you can also play games with small values of t, or run through t's for which the factors that divide those 3 numbers are limited. No, this is for any case. This is for, I mean, I did a generic case. You take an, no, this is always, this is the case for all t. Yeah, the nature of the primes of our reduction doesn't come in. I'm just saying that because this is the case, I can use that information to bound the shape of the bad Euler factors. So, I mean, let me just end with one data. So if you look at the quintic case, if you take the parameter psi to be minus 1, for example, as I was saying, then the conductor is 2 times 5 to the 5. If you take psi to be 2, n is 31 times 5 to the 5. And if a small values of psi, we actually, and this was computed numerically by verifying that the L function works. This is way beyond what people can compute with Siegel modular form. So these L functions in the case of the quintic should be the spinor L functions of Siegel modular forms of weight 3. And these conductors are way further than what they actually can compute on the automorphic side. So, I mean, there's one instance where I found in a different family one case of psi where the modular form appears in the literature, but that's an incredible accident. So I think to actually try to do the comparison with the automorphic side would be fairly difficult, because they're simply very hard to compute the other side. I mean, of course, the other side has enormous more information, but it would still be nice to be able to do that. All right, I'll stop here. Thank you.